Hey everyone, big day. So we're going to get into Earth's motions today. We're going to bring it in to the Sun, Earth, Moon system, and we're going to just start discussing the phenomena that are created by Earth's rotation. That's where we're going to hit first, and then we're going to move on to the phenomena that are created by Earth's revolution around the Sun. So normally we would spend a day on each one of these phenomenon because we'd be doing demos and using manipulatives and things like that. But obviously that can't happen. So we're going to do the best we can. And I'm going to explain to you what these phenomenon are and show you some videos and some animations and interactives that help visualize this because this is very spatial stuff. And so you're going to have to kind of put on your spatial thinking cap and really think about Earth's rotation. All right, and we'll get there. Okay, so here we go. I'm gonna move myself up here. Okay, all right. So first thing that we need to kind of remember is that when the Earth was formed, the matter that was in the solar system that was collecting via that force of gravity had rotational velocity. And when all the matter came together, the Earth kept spinning in the same direction in which it was formed. So when the planets formed, they were going around the sun, revolving around the sun counterclockwise when looking from above the sun's north pole. The Earth was, the matter for the Earth was spinning, again counterclockwise when looking from above the Earth's north pole. And when the Earth was formed, it was just a ball of magma, and that magma released gas, and that created our early atmosphere. And so we have this conservation of momentum, conservation of angular momentum. It's kind of like when gymnasts and figure skaters, they start spinning and their arms are out, and then when they bring their arms in, they spin faster, and then when to stop spinning, they move their arms further out. So it's that conservation of angular momentum that keeps the Earth rotating, that keeps the planets revolving around the sun. Okay, and we also have dated these rocks, and we know how long ago the Earth formed. So that's the formation of the Earth, the early atmosphere, and the rotational velocity of Earth. Okay, something that some of you are still having a problem with is the difference between a geocentric model and the heliocentric model. So the geocentric model said that the Earth was at the center of everything, okay? And in that model, the Earth didn't move. The Earth didn't revolve. The Earth didn't spin. The Earth sat still, okay? And everything else happened around us, okay? So that's the geocentric model, also known as the Ptolemaic model for the Greek philosopher Ptolemy. That model was wrong, okay? Galileo and Copernicus, they changed the model. So did Kepler. But Galileo and Copernicus were two of the first astronomers to use observations of celestial motions, of celestial objects, to say that, you know what? No, we're not at the center. The sun is at the center of the solar system. The sun god was Helios, so it's called a heliocentric model. Helium, okay, helium is one of the gases, the main gases that makes up the sun. Hydrogen's number one, helium's number two. Oh, excuse me, sorry. The heliocentric model is the correct model. The geocentric model is the old incorrect model. Okay, that's kind of important stuff there. You're going to actually learn about that next year in global. Okay, when you say global next year, they're going to talk about the scientific revolution and how the scientists were lambasted because of their proclamation that the Earth wasn't at the center of everything. Okay, it was sacrilege at the time. All right. Okay, so we're going to focus on the phenomena created by Earth's rotation. Let's just review a little about rotation. The spin of the Earth on its axis at a rate of 15 degrees per hour. Okay, now we know that the Earth is tilted at 23.5 degrees, okay, off of whatever. So we know that the Earth has a tilt, 23.5 degrees. I bet you guys never really thought about what that 23.5 degrees was in relation to, all right? But I'm going to explain it in 1 second, okay? So the Earth's axis, the North Pole, is always tilted. North Pole and South Pole is always tilted in the same direction as it moves around, as it revolves around the sun. So if this is the tilt of the Earth, okay, as the Earth revolves around the sun, that axis is always tilted the same way. This is called the parallelism of Earth's axis. And this is going to become really important when it comes to seasons. And that makes sense because the North Pole is always pointed at what? The North Pole is always pointed at Polaris. So if the Earth wasn't always, if the axis wasn't always parallel to itself, if it moved, it wouldn't always be pointed at Polaris. So the Earth's tilt is always parallel to itself. Okay, that's the parallelism of the Earth's axis. Okay. Now, what does it mean when we say that the Earth is at a 23.5 degree tilt? Okay. So we have discussed how the Earth's revolution around the sun is an orbit. Okay, the path is called an orbit, and we know that it's an ellipse now, right? Okay, but that's a line. That orbit is a circular line. Okay. A plane. What if we took a plane and put it through that path? Okay, so we took the plane, just like on the screen, and we took the path and we put a plane through it. Okay, a plane is a sheet of points. Okay. Well, the axis, if it was perfect, would be at a perpendicular angle to that plane. Okay, but it's not. Okay. It's tilted at an angle to that perpendicular. What is the degree of that tilt from here to there, to where the Earth's axis is? So this would be perfect. This would be a perpendicular axis, but the axis is not there. It's here. What is the value of this angle from there to there? The value of that angle is 23.5 degrees. That's the angle. Okay, that's the value of that angle. So here is the perpendicular to the ecliptic plane. It's called the ecliptic plane. That's the name of it, ecliptic, okay? Here is the actual tilt of Earth. That angle is 23.5 degrees. And note over here, the North Pole is pointed at Polaris. Over here, the North Pole is pointed at Polaris. In fact, if you took this Earth and put it anywhere on this path, that North Pole would be pointed at Polaris. Okay, so that is where the 23.5 degrees comes from. It's from this imaginary perfect perpendicular line that the axis would make if it was perpendicular to the ecliptic plane, to the plane of points that connect Earth's orbit. Alrighty? Okay, so here's another diagram of it. Okay, so there's the perpendicular to the ecliptic plane, and there's the actual tilt of Earth. Okay, and remember that the ecliptic is the plane that is created from the path that the Earth takes around the sun. Okay. All right, so I want to show you something before we move on. I want to show you this. Okay, so this is perfection. Okay, there's the ecliptic plane. That's perfection. This is just slightly tilted. That, 23.5. Oh, wait, let's get there. 23.5. Right, I can't get it. Right there, okay? That's the tilt of the Earth. What would happen if the Earth was even more tilted? The seasons would be way more extreme. Okay? If it was upside down, no, that can't be it, right? If the Earth was like that, then it would look like Uranus, right? Or Uranus rotates on its side. That's perfect. That is where we are, right in there, okay? All right? Okay, so let's go back to this. What phenomena does the Earth's rotation on its axis create? What exactly happens because of this rotation? This is a really cool video. Okay, this camera was set up to negate the effects of Earth's rotation. I want you to notice when it goes to nighttime. I want you to look, see how these stars are staying still? That's not what stars do. That's not what stars do to us, okay? Do the stars actually stay still? Yeah, okay. To us, though, they appear to rotate due to our rotation. Remember that? Remember from mapping when we did the circumpolar star lab? All right. So this camera was set up to negate the effects of Earth rotation, to negate the sun rising and setting, to negate the stars from circling in the sky. All right. So what actually happens? Okay. First things first. remember in the geocentric model, the Earth didn't rotate. And people had to accept the fact that Earth was rotating, even though we couldn't see it rotating, couldn't feel it rotating. And there were no satellites, there were no planes, there was nothing that could prove it. So many experiments were attempted to prove that the Earth rotated, and none of them were successful until Léon Foucault. He came up with Foucault's pendulum. Okay, so if you remember from learning about, I think you learned about it in 6th grade maybe, Newton's 3 laws. Okay, the first law is the law of inertia. An object will continue to do what it's already doing. So an object in motion will stay in motion at the same speed and in the same direction unless acted upon by an outside force. Okay, so he said, what object could I get to stay in motion and it would stay in the same plane and Earth would move under it? Well, he figured if he set a really big pendulum in motion, okay, the pendulum would hang on a ball and socket joint. So like this would be the thing that was attached to the building. And then the string would be attached to one of those sockets, like on a hitch, a trailer hitch. And that could, like your shoulder, that could turn, right? So the pendulum would be hanging on this and swinging back and forth. And it could turn independent of the building, okay? So it could just do that. And what happened is he set the pendulum in motion, and the pendulum stayed in the same plane. But what did the Earth do underneath the pendulum? The Earth rotated, and everyone in the room, on the Earth, in the building rotated. So what they thought they saw, was the pendulum changing directions. But the pendulum didn't change directions because of Newton's first law. An object in motion will stay in motion at the same speed and in the same direction unless acted upon by an outside force. And there was no outside force acting upon it because it was in that ball and socket thing. So the pendulum stayed in the same direction, and the room, the Earth, rotated underneath it. So if you ever went to a science museum, you may have seen a Foucault pendulum. I'm going to show you a video in a second. Now, this was, the first experiment that proved the Earth rotates. This is proof positive that the Earth rotates. So if you're ever asked, hey, what's that thing that can prove Earth rotates without us going into space? Oh, Foucault's pendulum. First experiment that did it. And it was in 1851. It was very revolutionary. This experiment disproved, finally, once and for all, disproved geocentrism, because in the geocentric model, the Earth doesn't rotate. And this experiment proved that it did rotate. Okay? All right, so, oh wait, I want to go back here. I just want to show you. Okay, this is a picture of the Foucault pendulum. Now, in many pictures, you're going to see these pins. Okay, so these pins are all the way around the whole circle. Okay, and if you notice over here, you see these pins over here are standing up, and these pins over here are standing up, and you see these pins in the foreground are standing up, but these are knocked down. So what's happening is this pin right here, this pin here that was there, was the one that was knocked down most recently. And this pin over here, that one didn't get knocked down, but this pin over here was knocked down. So what are the next two that are going to get knocked down? This one right here, and that one right there. Okay? So as you hang out, if you hang out for like a half hour, you can actually see the pins getting knocked down because the pendulum swings very slowly. Okay? Oh, let's go back. Hold on. That's Curiel. I'm not going to watch that for a second. Okay. So I want to go here. Okay. This is a video of Foucault's pendulum swinging. And this family hung out. It's actually pretty funny because the kids are like, oh, you know. So here you can see, now these pins are on little pivots here. So all these pins were knocked down here. And all those pins were knocked down back there. And then this is going to be the next guy to get knocked down. So you can see them all knocked down. So that one's next. This one's really close. So you can see it's about an inch away. Oh, so close. Let's speed it up a little. A little bit. A little closer. Ooh, so close.
That was close.
Because seriously, it only knocked down like once since we walked into the museum. I'll just like it took a half hour. It's just so.
Hit it.
It tipped it. It tipped it. A little bit.
Pay attention.
Oh, see? It's touching it. It's touching it. Oh, wow. Oh. At least it's made contact. Yeah.
Silver.
Oh! I knocked it over. I didn't see it.
Okay. So that was Foucault's pendulum. Okay. So another, this is tough. Coriolis effect. Okay. Coriolis. Okay. Another French dude in 1835. He's given that his honor was to use his name to name this phenomena. Okay. The Coriolis effect is essentially the deflection of fluids. It could be air or water, okay, moving over large distances, or objects, projectiles moving over large distances, and they are deflected to their right in the northern hemisphere and their left in the southern hemisphere. You may have heard, toilets in the northern hemisphere drain counterclockwise and toilets in the southern hemisphere drain clockwise. That's not true. The direction that a toilet drains or a tub, you know, when you're in the tub when you were little and water would go down the drain, that is not a large enough area, large enough distance for it to flow over. And that is mainly controlled by the shape of the bowl, the shape of the drain, and the direction that the pump pumps the water in. The Coriolis effect is only for free-flowing liquids, air or water, so air currents and water currents, or projectiles, planes, or rockets, etc., flown over very, very large distances on Earth. And it's essentially due to the spinning of the Earth and the difference in velocities at different latitudes on Earth. Okay, so here's how it works. Okay, we know that no matter where you're standing on Earth, if you're at the North Pole, if you're in the Arctic, if you're in mid-latitudes, if you're close to the equator, on the equator, wherever you are on Earth, every single person, every single place is rotating at an angular velocity of 15 degrees per hour. We have studied that. We know that it's 360 degrees in 24 hours, and we got 15 degrees per hour. That's the angular rate of rotation. So again, it doesn't matter where you're standing on Earth. Everyone rotates, every place rotates at 15 angular degrees per hour. However, that's angular distance, not linear distance. So to cover that 15 degrees, if you're at the equator, you're going 1,600 kilometers per hour to cover that 15 degrees. If you're in if you're in northern Mexico or southern United States, you're going about 1,400 kilometers per hour. If you're in northern Canada, you're going 800 kilometers per hour. And if you're at the North Pole, you're going 0 kilometers per hour. Okay, because here you're covering more distance in the same amount of time. All right, that gives you a different lateral velocity than other places north or south of you. Okay, so if you were to throw something from the equator and throw it northward, you'd be throwing it due north, but it would also have an angular component to the right. Okay, if you were to throw something south, you'd be throwing it south, but it would also have an angular component to the left. Okay, so I can't explain it as well as this next video does. So take a look at this. This is pretty short. By the way, this does explain why the meteorological effects of the Coriolis effect. So it explains why hurricanes rotate one way in the northern hemisphere versus the southern hemisphere. So this is how it applies to air currents. Okay, all right.
If you've ever watched the news during a hurricane or wintertime nor'easter, you've probably noticed that big storms spin over time as they travel. In the northern hemisphere, they spin counterclockwise. But if you were watching a storm in the southern hemisphere, you'd see it spinning clockwise. Why do storms spin in different directions depending on their location? And why do they spin in the first place? A storm's rotation is due to something called the Coriolis effect, which is a phenomenon that causes fluids like water and air to curve as they travel across or above Earth's surface. Here's the basic idea. Earth is constantly spinning around its axis from west to east. But because Earth is a sphere and wider in the middle, points on the equator are actually spinning faster around the axis than points near the poles. So imagine you were standing in Texas and had a magic paper airplane that could travel hundreds of miles. If you threw your airplane directly northward, you might think it would land straight north, maybe somewhere in Nebraska. But Texas is actually spinning around Earth's axis faster than Nebraska is, because it's closer to the equator. That means that the paper airplane is spinning faster as well, and when you throw it, that spinning momentum is conserved. So if you threw your paper airplane in a straight line toward the north, it would land somewhere to the right of Nebraska, maybe in Delaware.
Deflected to its right. Deflected to its right.
So from your point of view in Texas, the plane would have taken a curved path to the right. The opposite would happen in the southern hemisphere. An object traveling from the equator to the south would get deflected to the left.
It's left.
So what does this have to do with hurricane spinning? Well, at the center of every hurricane is an area of very low pressure. As a result, the high-pressure air surrounding the center, or eye, of a storm is constantly rushing toward the low-pressure void in the middle. But because of the Coriolis effect, the air rushing toward the center is deflected off course. In the northern hemisphere, the volumes of air on all sides of the eye keep getting tugged slightly to the right.
To their right. So if you notice, this parcel of air right here looks like it went to the left, your left, but it didn't. It went to its right. So if you're the air, it's going to its right. So no matter which air you were here, which parcel of air you were, each parcel of air is going to its right. Even though it look like to you, it looks like you are left, but it's going to its right. Okay, that's really important.
The air keeps trying to make its way to the middle and keeps getting deflected, causing the entire system to spin in a counterclockwise direction. In the southern hemisphere, where the Coriolis effect pulls air to the left, the opposite happens. Storms spin around the eye in a clockwise manner.
All right, so basically, Coriolis effect is quite complex. All right. But basically what you have to understand is that any air or water or projectile in the northern hemisphere is going to veer towards its right. And in the southern hemisphere, it will veer towards its left. So air, water, projectiles in the southern hemisphere left, northern hemisphere right. Southern hemisphere left, northern hemisphere to their right. Okay? And again, what is this a phenomenon of? This is a phenomenon of Earth's rotation. And again, we would be getting into way more detail about this if we were still in school, but just kind of take it for what it is and just kind of take it in and just say, okay, northern hemisphere to the right, southern hemisphere to the left, and that's why hurricanes spin different ways. And it's a phenomenon of Earth's rotation. Okay? All right. Okay, solar time. We've talked about this, all right? Solar noon varies depending upon your longitude. This is a phenomenon of Earth's rotation, dark, light, day, night, solar time. Been there, done that, okay? This measurement is based on the apparent movement of the sun through the sky. Now, what we're going to do when we hit revolution is we're going to start talking about sun path, okay, and how that affects seasons. If you've been noticing, the daylight hours have been getting longer, the nighttime hours have been getting shorter, and that's a combination of a phenomena created by Earth's rotation and revolution. Okay. All right, we know that the Earth spins 15 degrees per hour. We know about time zones. That's old news. Old news, okay. Stars' apparent paths across the sky. We hit this too during mapping. This is a phenomenon of Earth's rotation. So because of the rotation of Earth, the stars appear to move in circular patterns across the sky. The one star that doesn't appear to move is Polaris, and that's because it's directly above our axis of rotation, okay. Stars rise in the east, set in the west, just like the sun does and the moon. All right, because of Earth's rotation, the stars and constellations appear to move at a rate of, everybody, 15 degrees per hour. All right. Constellations appear to move around Polaris. Okay, if they're out all day and all night, all year, they're called circumpolar constellations. Okay, the biggest one for us is Big Dipper, right? Okay, here are star trail photos. What star is in the center of each one of these photos? So what star is that? What star is that? And what star is behind that cactus? One star that doesn't move. Polaris, you got it. What compass direction was every single one of these cameras facing? Psst. Polaris's other name is the North Star. North, you got it. And tell me about this photo. Polaris seems to be just above the observer's horizon. So this camera was very close to the equator, right? Okay. And here's a cool video of star trails. So what I want to focus on here is how star trails look facing north, how they look facing east, west, and south, because they look very different. Remember that stars, along with planets and the sun and the moon, rise in the east and set in the west, okay? So this is a pretty cool video. Only 2 minutes long. These are the moving stars in the northern hemisphere. We're looking west now to the setting sky. So you see how the stars are coming from here and they're setting in the west. That's the Milky Way. We're facing west and we can't see Polaris. Polaris is somewhere up here. Now, this is how the star trails look when you're looking west. So you can see Polaris is up here. So imagine you're facing California. You're facing west. Okay, so you're facing California. Where is north? On your right. So we're facing, look at the screen. We're facing west. Where's Polaris? On our right. Okay. Now, when you're looking west, the stars come from the top left and move down to the bottom right. So if you see star trail photos that don't have that circular pattern and they start at the top left and go to the bottom right, you're facing west. Okay, so now you're standing in America and you're facing the East Coast. You're facing the East Coast. Where's Canada? On your left, so that's north. Okay, so you're facing east. Oh, there's Polaris in the north. Okay, so when you're facing east, the star trails come up from the bottom left and go to the top right. Okay, so those are star trails when you're facing east. And this is, again, phenomenon of Earth's rotation. Circumpolar picture. I love this. There's Polaris in the middle, right? Isn't that great? So we know we're facing north because we can see Polaris. We're rising to 11 degrees south and you do a time lapse, they look arcs because they rose over here, they went into your southern sky, and then they set in the west. So star trail photos look very different when you're facing different compass directions. Okay. So, gotta get rid of it. Okay, so here's a still photo, and we're looking at the celestial equator. So where's north, left or right? Okay, so remember, they're starting at the bottom left, they're going to the upper right. Are they rising or setting? They're rising. Okay, so if we're facing east, we're facing the east coast of the United States. We're standing in Kansas, we're facing the east coast of the United States. Where's Canada? On our left. So north is to the left up here. And this is south, and that's where they're going to arc across the screen, right? So again, why do the stars appear to move? Because this is a phenomenon based on Earth's rotation, because we're rotating under them, okay? And we know that the Big Dipper never sets, and because it's circumpolar. And we know about the pointer stars, okay? This was Double Jeopardy on May 10th of last year, and I took a picture of it because this was, imagine getting this for Double Jeopardy and you bet it all. You'd be like, yeah, Earth science. Okay. The Drinking Gourd was the group of stars that helped runaways find the North Star in the night sky. Was this group of stars? What was it? The Big Dipper. You got it, because here we go. Here's the Drinking Gourd. Okay, here's the pointer stars. Remember Doobie and Merak? And they point to Polaris, and no matter where it is, no matter where that Big Dipper is in the sky, if it's to the right, to the left, bottom, top, whatever, we can find Polaris. All right. Here is the entire night sky, and the Big Dipper is, hold on, wait for, here's the Big Bear. Okay, so here's the Big Bear. Okay, and here's the Big Dipper right here. That's his butt and his tail. Remember, the Big Dipper is an asterism, not a constellation, because it's part of a bigger constellation. And here are the pointer stars. And they point at Polaris, and this is the Little Dipper right there. Okay. Okay. So this is a VIF. The apparent motion of the stars is due to Earth's daily rotation on its axis. The stars don't move. We do. We move under them. Okay. But you already know that the stars are moving because you picked stars that were in our neighborhood in the Milky Way. And what are we doing with all of our neighbor stars? We're revolving around the Milky Way. So are the stars actually moving through the galaxy? Yes, we're moving with them. We're all kind of moving as a cohort, right? So in our lifetimes, the positions of the stars don't appear to really move, okay? It's kind of like this. You know when you look up in the sky at a plane and you know it's going 600 miles an hour, but you look at the sky at a plane, it's like, wow, it looks like it's hardly moving at all. Like it's going across the sky. It's moving, but it's moving really slowly. You know it's going really fast, but it looks really slow. It's because it's really far away. But if that plane was like only, you know, a couple of 100 feet above you and was going 600 miles an hour, you'd be like, whoa, because it was going really fast and it's close to you. It's kind of like the stars. The stars are so far away from us that even though they are moving relative to us, in our lifetimes, even in thousands of years, they appear like to not move at all. So this shapes the constellations stay pretty much put to us, okay? But scientists can track their motion and they know how they've changed. So here's the cool thing. Okay, here's the Big Dipper as we know it today. This was the Big Dipper 100,000 years ago. Kind of looks like the big spatula, doesn't it? All right. And this is what they think the Big Dipper is going to look like 100,000 years from now. Because the stars are moving relative to one another. Again, it's just so slight to our perspective that they will change position. So this will be what it looks like in the future, which is a little sad, okay? But that's how it's going to look. And there's a pretty cool... No, I don't want to do that. Here, I want to do this. Okay. There's a pretty... Oh, go away, please. Oh, I got to get rid of that. Okay. No, thank you. Oh, boy. Okay, not this one. No, not that one. Here we go. So here's the Big Dipper. Okay, moving around the Little Dipper. Now, look what I'm doing. I'm moving the months of the year, right? So if you go out right now, it's the end of May, beginning of June, and you go out at 9 p.m. Wait, where am I? PM, 6 p.m. Oh no, 6 p.m. Okay. You go out and when you go outside at like 9 o'clock, that's where it's right above you. The Big Dipper is pretty much right above you, right? But if you go out at the same exact time in the winter, well, the Big Dipper is really low in the sky. Okay, so we know that the Dipper rotates based on Earth's rotation, but its relative position changes because of rotation and revolution. Okay, so the Big Dipper rotates around Polaris once every 24 hours. Okay, but the position of it also changes due to Earth's revolution around the sun. Okay. And finally, and this is the tough one, the sun's apparent path across the sky. The sun's apparent path across the sky is where the sun rises and sets. Now, the sun rises in the east and sets in the west. It doesn't rise due east and set due west every day. It only does it twice, 2 days a year, okay? The altitude of solar noon, how high the sun is in the sky, also changes. But we know that the path of the sun moves across the sky because of Earth's rotation, okay? But why does this happen? I just want you to look at the summer solstice. That's coming up now. Look at the North Pole, 24 hours of light. And this is winter solstice. Look at the North Pole, 24 hours of dark. Summer solstice, winter solstice. Now we know that day-night line is moving because of Earth's rotation, but why does the length of day change? Why do we have seasons? Okay, why does that happen? And that's revolution. That's when revolution and rotation come together. Okay, and that's what we're going to hit next. Okay, so these were all the phenomena based on the phenomena created by Earth's rotation, and this is what we're going to get to. Oof, that's tough. Okay, what we're going to do is we're not going to hit sun path the way we do normally. Okay, because sun path is hard. Okay, and you don't have the materials at home to do that. But what we're going to do is we're going to talk about sun path in terms of seasons, because we're going to hit the phenomena created by Earth's revolution next time. All right, so I know this was kind of long, and I'm going to give you some work to do to reinforce this. All right, not much, but we're going to get to the good stuff. What causes seasons? And then we're going to get to the moon's phenomena. So we're going to get to eclipses and phases and tides. Okay? All right, guys, I'll see you next time. Take care.